All right, so we're going to try this video again. For some reason, it hadn't been uploading. So we're talking about relative motion and independence of vectors. So relative motion, previously we defined motion as position changing with respect to a reference point. So that basically means is when you're looking at something move, you're comparing it to something else, whether that be something standing still, another object, okay, but you're comparing it to a reference point. But all motion is relative. Basically, that means is it can always change based on who's observing it. Okay, so that means you could see something different than I could. So motion is relative to the reference point, so what you're looking at, and the frame of reference of the observer. So that means basically where are you and what is your frame of reference when you're looking at this motion. So observers in different frames of reference can view motion differently. Okay, so you can see something differently than I could based on where we are. Now, motion of automobiles is usually with respect to the ground. Okay, so we're usually comparing, when we see a car drive by, you're comparing it to objects that are around it. Okay, especially the ground because it's stationary. But it's going to be viewed a little differently for a moving observer. Okay, so we'll take a look at the example. Is a stationary observer, so someone standing still sees a car go by at 60 miles per hour. That means they're going to see it go by at 60 miles per hour. They're not moving, so nothing's really changing. Now, as soon as you start adding movement to it, now it can kind of affect things. So if I take that observer and I put them in a car that's going 20 miles per hour to the right, and then that same car is going 60 miles per hour to the right, okay, now that frame of reference is going to change a little bit. So the way I think about this is when you're on the highway doing about 70 miles an hour and someone passes you going 80, it doesn't really look like they're going 80, they're just slightly going faster than you are. So to you, it would look like they're going 10. Okay, so in this case, it's going to look like they're going 40 miles per hour since you're moving with them. Now, if you take that same car that's going 20 miles per hour, okay, and move it the opposite way, and the other car is still going 60 miles per hour, okay, now it's going to look like they're going 80 miles per hour because you're going opposite directions. Okay, we didn't change the speed of the car at all. We just changed our reference point each time. Now, a boat's moving down a river at 8 meters per second to the north, so we're going 8 meters per second to the north, and a person is on the boat walking towards the front of the boat that's also going to the north at 2 meters per second. Now, if you were asked what does a person on the boat view his or her velocity as, so the person who's actually walking, and you ask them how fast are you walking, they're not going to really take the reference of the they're not going to really take into account the velocity of the boat. So think about it like this way: when you're on an airplane's going like 500 plus miles an hour up in the air, and you walk to the bathroom, it doesn't feel like you're walking to the bathroom at 500 plus miles per hour. It just feels like you're walking whatever you're walking. So the person on the boat, to them, they only feel like their velocity is going 2 meters per second. Now, if you were to take an observer and put them off to the side on the shore, and they see someone walking towards the front of the boat while the boat's going 8 meters per second to the north, okay, now you'd combine those. The way I think about this is those moving walkways that are at the airport. Okay, so like you see a person walking normal, and all of a sudden they step on one of those, and it looks like they're walking even faster now because you combined their velocities. So the person on the bank is going to see the person's velocity as 10 meters per second. Now, a boat crossing a river 8 meters per second to the north. So what I'm going to do is I'm going to draw a river. Okay, so it's going to be a very basic river, and I have a boat, and this is a very basic boat. Okay, this is like a bird's eye view. So we're looking down. I have a boat going across the river at 8 meters per second. Okay, the current is pushing the boat downstream at 3 meters per second. Okay, so what's going to happen is we want to know what is our overall velocity as the boat's being pushed this way. So if you notice, that's going to create a triangle. Okay, so now you can draw your triangle two different ways. You can close it off here, or you can close it off here. Okay, so the triangle I used is going to look like this. Okay, so there is no wrong way. So I'm looking for my angle. Okay, I know my vertical is 8 meters per second. My horizontal is going to be 3. And we want to know what is this resultant velocity right here. So if I have two sides of a right triangle, all you got to do is Pythagorean Theorem. So this is stuff we've been doing. So square root of a squared plus b squared. So 3 squared plus 8 squared. And you'll get a resultant velocity of 8.54 meters per second. Okay, now that's part of your answer. Now we got to find our direction. Okay, if I were to look at my triangle, I have my opposite, which is 8. I have my adjacent, which is my 3. Okay, the only trig function that uses both those is going to be your tangent. So tangent of your angle equals opposite, 8, over your adjacent, which is 3. I'm going to move that tangent over. Okay, I got to make that angle by itself. Okay, so when you do that, it becomes inverse tangent. So it becomes tangent with a -1. So you just press second tangent on your calculator. And you're still just going to type in 8 divided by 3. Just make sure you're in degree mode on your calculator. Otherwise, you're going to get a different answer. So you're going to get 69.44 degrees north of west. Now, the reason why it's north of west is it's touching my west line, okay, and then going north of it. Okay, so whichever line it's touching, that's the last letter. So if it's touching west, that's the last letter. Okay, now if you drew your triangle the other way, okay, so say your triangle went up and then to the left, okay, your angle is going to be different. Your angle would be 20.56 degrees west of north. So again, we'll accept either one of those, it's fine. Okay, now what we're going to do is we're going to see is if we increase that current, the boat's velocity, we're going to keep the same, but we're going to increase the river current 5 meters per second to the west. We're going to see how that's going to change things. Okay, so we're still going to have our same triangle. Okay, so my boat's going to cross at 8, but now my river's going at 5. So we want to know what is going to be my new resultant and my new angle. Okay, so we're going to do our same Pythagorean theorem. So square root of 8 squared plus 5 squared. And you're going to get a VR of 9.43 meters per second. So that did affect our resultant. So now we're going to see what our angle is. So we're going to go ahead and do our inverse tangent of opposite over adjacent. So 8 divided by 5. Okay, and you're going to get a new angle of 57.99 degrees north of west. Okay, so that did affect our angle. And if you did the other triangle, your angle would be 32.01 degrees west of north. Okay, now would the increase in velocity, the current, and overall velocity affect the time it would take to cross the river? So this is where you got to think about is, this is a hard concept to think about, is yes, our resultant velocity changed, but that's because you're combining vertical and horizontal. But did we ever change the velocity of the boat going across the river at 8 meters per second? No. Did we ever change the distance, the width of the river? No. Okay, so the only thing that's actually going to tell you how much time it takes to get across the river is just the velocity going across the river. It's not the hypotenuse that we just found. Okay, it's just the velocity going across the river. And if none of those changed, your answer would be no. Okay, because perpendicular vectors are independent. That means north and south do not affect east and west. It can push you off track a little bit, yes. Like think about if you're running on the track. If you're running forward and you have wind blowing with you, it's going to make you run faster. If you have wind blowing against you, it's going to make you go slower. If you have wind pushing to the side, okay, that's not helping you or hurting you. It's not speeding you up. It's not slowing you down. Now, could it bump you off track a little bit? Yeah. Okay, but that's not helping your speed or hurting your speed. So that's what we mean by if they're perpendicular vectors, they do not affect each other because they're not on the same plane. So perpendicular vectors are independent of one another. So north and south does not affect east and west. If one component vector changes, it affects the resultant. So it did affect the hypotenuse that we found and the angle, okay, because you're changing one of the pieces there. Okay, but it does not affect the other perpendicular component. So when we change the river velocity, it didn't change our boat's velocity at all. So that's what we mean by perpendicular vectors are independent.